Welcome to Mahatma Education Society's e-learning channel. This is the 7th of a series of videos on Introduction to Mechanical Vibrations. We are in the chapter of Basic Concepts of Vibrations. The outline of the lecture will be the recapitulation of last lecture. How does displacement versus time curve changes with initial conditions? Plots of displacement, velocity and acceleration with respect to time of simple harmonic motion and also in rotating vector form. Then representation of simple harmonic motion in complex form, and finally we end up with one numerical solving. The recap. So we saw why the simple harmonic motion study is important, right? So one of the reasons was most of the systems in practical nature, they closely follow the simple harmonic motion if we are assuming that the displacement is very small, right? So we convert non-linear problem in terms of a linear problem. So we closely approximate the simple harmonic motion. The same we do for mechanical vibrations. And the second reason is this study of simple harmonic motion enables us to build up various basic shapes of different frequencies into a complex periodic motion by the use of Fourier series. Then we saw the classification of vibrations. Then we saw the steps involved in vibration analysis. Basically they are 3 in number. First was the mathematical modeling, in which we get the schematic model of the real vibrating system. So we can have different schematic models created, and we cannot say that our schematic model is right and the other one is wrong. So it can be logically constructed, and it is an art and changes from person to person, and has different perspectives. So as a designer, we start with the lowest degree of freedom so that we get a fair idea of the value of the omega n, and we can solve the equations very quickly in less amount of time, and then slowly we build up the complexity of the schematic model so as to increase the accuracy of omega n's, the lower values, but it will also lead us to a increase in the complexity of the results, right, complexity of the calculations, right, and it's a trade-off or a compromise between the accuracy involved and the complexity of the calculations or computation costs. So depending on that, we try to solve the model the real system, and we get the differential equations from these free body diagrams of the schematic models, and then in the step number 2 we try to solve it using mathematical tools such as matrices, right, and then we have these eigenvalues and eigenvectors, which give us the estimate of the natural frequencies and mode shapes. And in the step number 3, we have to interpret the solution, and we have to check whether the solutions obtained are within the limits or acceptable to us or not. If it is not acceptable, we try to change the design, something like the material or the dimensions and so on. Okay, and lastly we saw how to add harmonic motions of the same frequency, and we got the resultant to be of the same frequency and also of a simple harmonic form, and it applies to n number of harmonic motions of the same frequency. Now, how does displacement versus time curve change with initial conditions? So what are initial conditions? Initial conditions are nothing but the disturbance given to the system so that some energy is induced in the system so as to initiate the vibrations, right? So we have x0 and x dot 0 initial displacement and or initial velocity. So let us have some combinations of these. So I have x0 and x dot 0, they can have different values, and let us give some number to it. Let us have say 1, 2, 3, 4, 5, 6, 7, 8. We have 8 combinations here. Let us number this. So let us say that x0 and x dot 0 both are positive initially, then positive, negative, positive, 0. Similarly, negative, positive, negative, 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 0, and 0, positive, 0, negative. So let us see how does the curve looks like, right? So in the first case we have positive displacement and positive initial velocity, so that will be something like this, right? So this is amplitude A, so I can mark over here, this is x0, displacement at time t equal to 0, and for velocity we have to refer to the slope, the tangent line drawn over here. So if I take the angle over here, theta, at time t equal to 0 here, right? So this if I take the tangent of this angle, basically I am getting the slope, right? So it is basically x dot 0 refers to the tangent of this angle, right? Both are positive, so it is parallel, it is going upwards, right? Like a staircase going upwards, it is having positive slope. The second combination is positive and negative, so I am having a positive displacement, initial displacement, and it's a case of negative velocity. So tangent drawn over here is indicative of the negative velocity, right, while the displacement is positive, right? And third one is positive and 0, so you can have something like this, okay, that the slope at this at the start of the curve is horizontal line, right? So it is a 0 slope, so x dot 0, right, is having a 0 value while there is some value of x0. The fourth one, negative and positive, so you can keep drawing this one, so negative and positive, something like this, right? Then fifth one, you are having negative and negative, negative and negative slope, something like this. Sixth, negative and 0, something like this. So this is a minima curve here. Then seventh, 0 and positive, so 0 displacement and positive initial velocity, something like this. So we normally try to draw the oscillations. Initially we have drawn using this particular plot, displacement versus time plot. It is actually a specialized case of displacement where the initial displacement is 0 while the initial velocity is positive. So I can say that whatever displacement equation I am using, so this x of t is equal to a sine of omega t, it corresponds to this particular case. It is not general as such, it is specific in nature, corresponding to this combination, 0 displacement and positive initial velocity, right? So we will try to modify this for the general case shortly. So the final one will be 0 and negative, so 0 displacement and negative velocity, something like this. So if we look at all these plots, you will observe that by a different combination of initial displacement and velocity, I have a change in the value of the phase difference or phase, okay. So this occurrence of the cycle is changing with respect to a change of initial conditions, right. So this is a special case where initial displacement is 0 but velocity is positive. So I will modify the displacement equation so as to incorporate any kind of plot, that is something like this, a sine of omega t plus phi. So phi is some unknown value of the phase difference, right, and a also is unknown for now. So these values will be known to us when we incorporate the actual values of initial conditions in this equation. This is 1 for displacement, then we take the derivative of this and then we put up x dot 0 in this equation for time t equal to 0, and then we can find what are the values of a and phi, right. So you can sum it up all these plots together just by drawing one curve, right, and the ordinate can be shown at different locations in this curve, right. So for the first case, positive and positive, it should be somewhere where over here, so number 1. Second case, positive and negative, so positive and negative somewhere over here, it is case number 2. So time t equal to 0 starts from here, so ordinate should be drawn over here. Third case, positive and 0, so positive and 0 means the maximum over here, third case. Fourth is negative and positive, so negative displacement and positive slope somewhere over here. Fifth one is negative and negative, somewhere over here, fifth. Sixth is negative and 0, so negative and 0 is something like this, sixth, sorry. Then seventh is 0 and positive, so 0 displacement and positive, that is the starting point over here, seventh. And eighth one is 0 and negative, so that will be the over here, this is eighth. So can sum up all these plots in one plot over here, one diagram, so it will be easy for us to understand. Now, how to plot this displacement, velocity and acceleration curves with respect to time. So also in rotating vector form for simple harmonic motion. Now suppose I am assuming that x of t is equal to a sine of omega t, the special case, right. So let me draw the rotating vector form, something like this, right. This is a reference axis from where the angle is measured, and all the actual values will be plotted on the y axis. It can be any parameter here. So starting with the displacement, so this is a vector a, right. So the curves will be, okay, initially this will be for displacement, function of time versus time here. So the limits are, so sorry about this drawing, so it should start from t equal to 0, something like this, okay. So when time t equal to 0, the point A is over here, then it starts rotating like this, okay. So this is value is a sine of omega t, the curve is something like this, and if I take derivative of this, I will get acceleration. So let us not show this t over here, it should be omega a cos omega t, which can also be written as omega a convert to sine omega t plus pi by 2 radians. So it is occurring at 90 degrees earlier than the displacement. So I am having a velocity occurring earlier than displacement, so this one is displacement, I am having velocity occurring earlier, and if I separate the sine term or cosine term, what are we having is omega a, which is nothing but the maximum value of x dot, right. Sine and cosine gives us the variation between 0 to 1, so omega a is the maximum value of x dot, right, that is amplitude for velocity, okay. So this should be omega a, and for this particular time I am having is over here, so the circle for velocity, and these are the limits for velocity. I will just take it over here, and so where are we now? So it is something like this, it should be starting from here, right. So for t equal to 0, the displacement point should be over here and velocity should be over here, starting from here, so it should be like this, right. So this phi should be 90 degrees for the velocity. So this is velocity versus time plot, right. Then this value is omega a, and lastly I am having x double dot as it is minus omega square times a, right, sine of omega t, convert minus in terms of plus, you can have omega square a sine of omega t plus pi radians, right. So again I am having a change in the phase angle here, right. So x double dot compared with x is occurring earlier than the displacement by a value of pi radians or half cycle, so that confirms that the acceleration is directly proportional to displacement, but it is directed opposite. So this is omega square a, and it is having a bigger radius, bigger circle now. So this is the direction of acceleration. So wherever displacement is there, acceleration is pointed opposite. right? So I will just take this, so it is a bigger circle, right? Something like this, and yeah, something like this. So this should be acceleration versus time. So it is exact mirror image of displacement. It should start from something like this, okay? So this value is omega square a, that is the coefficient of sine term, which is the maximum value of acceleration or the acceleration amplitude. So this is the rotating vector form of simple harmonic motion, vector form of simple harmonic motion, right? And these are parameters with respect to time curves separately drawn, right? So I think the concepts are clear to you here. Now how do I represent simple harmonic motion in complex form, right? Complex notation. So I'm having the real axis and imaginary axis, right? And I show the vector amplitude a theta is equal to omega t. So I'm having the x component capital X, let us say, y component capital Y. So I can say the displacement is equal to x component plus the imaginary number times y component. So it is a cos of omega t plus I times a sine of omega t. So taking a common outside, it is cos omega t plus I sine omega t. So it is a expansion of e raised to I omega t. So this is omega t is nothing but theta. So it is a times e raised to I omega t, or it is a e raised to I theta. Okay, so you can also include the phi over here. So instead of omega t, I can write omega t plus phi and sine of omega t plus phi, and this becomes here theta plus phi likewise. Okay, so that phase can be included, right? So this is called as the Euler's notation. Euler's notation, right, for simple harmonic motion. So this also is very compact in nature, right? So if I use this form so as to get the differential equation, let me see what do I get. So if x is equal to a e raised to I omega t, then x dot should be equal to I omega is the coefficient of this a e raised to I omega t. Then x double dot should be coming as I square omega square a e raised to I omega t. Now I is root of minus 1, so I square is minus 1, so minus omega square, then a e raised to I omega t. So a e raised to I omega t is nothing but x. So I'll just write here instead of this x. So I'm having x double dot plus omega square x equal to 0, right? So here I'm also having the acceleration directly proportional to displacement, but opposite in direction, that's why it is minus here, right? So basically I'm having the same differential equation of simple harmonic motion as I had got earlier, right? Now you have three different forms of the solution. I'll just write over here before proceeding with the numerical. So you can have x of t as a sine of omega t plus phi, the general equation, or you can have x of t as a cos of omega t plus phi, and there's one more equation. So let us see the equivalence of these equations in the coming lectures, say in chapter number 2. So I'm having the third one as x of t is equal to a sine of omega t plus b cos of omega t. So we will see later that all these three equations are equivalent. Okay, so for this particular numerical, you can start with any of these three equations, and you have to find the value of the unknown constants a and b in the third equation, the value of a and phi in the first and second equations. So note that here this a and phi may be different than this a and phi in the second equation. Okay, so this will be found out, constants, unknowns will be found out from the initial conditions of the given problem, right? So in this numerical I am having a linear frequency as 5 Hertz. So we convert that in terms of omega. So what is the formula here? Omega is equal to 2 pi f. So you can get the value in radians per second, right? Initial displacement is given 1 centimeter, so that is x for a value of time t equal to 0. So you can write in SI units 0.01 meters, and initial velocity is given, that is x dot at time t equal to 0 is 6.28. It is given in centimeter per second, so you can just multiply by 10 raised to minus 2 meters per second. So remember, we are going to use SI units here, right? So you are required to find out the amplitudes and phase of displacement, velocity and acceleration. So basically the value of a, then omega square a, the amplitudes for each of these parameters need to be found out, right? And then you have to plot the same. So this plotting can be done by yourselves. You know how to do it now, right? Now I will just discuss how to get these values, the values of the amplitudes. So what you do is, you have to start with any of these three equations. Let us say I am having the first of the equations, x of t is a sine of omega t plus phi. Then take the derivative of that, right? It is omega a cos omega t plus phi. Now you introduce the initial conditions. So you have to keep time t equal to 0, and this value becomes x0, right? So it is a into sine of phi, and for this time t equal to 0, I am having x dot 0, which is given to you, is equal to omega a, right, into cos of phi, right? So in this equation, what you can do is, you can take x dot 0 upon omega as a cos phi. So let us take it as 1. This is the second equation. Now what you can do is, you can take 1 square plus 2 square. Okay, so a square sin square phi plus a square cos square phi. So a square is common, sin square plus cos square is 1. Okay, so that is what you can do. So we will get the value of a, and for getting the value of phi, what you can do is 1 divided by 2. So we are getting sin upon cos, sin divided by cos is nothing but tan. So phi is equal to tan inverse, right? So what answer you are getting at the end while you do the calculations is equal to 0.0101 meters, and you have the value of the phase difference as 78.696 degrees. So what we have seen in this lecture is how to plot the displacement, velocity and acceleration curves of a simple harmonic motion, also in rotating vector form, right? We have seen how to obtain the displacement versus time plot for different values of initial conditions. It can be positive, negative or 0. So for various combinations of initial conditions, how does it make a difference in the plot, right? So that we have seen, and that is very fundamental to our understanding of this subject. Then we saw this numerical, and hope you have understood the contents, right? So just remember these three equations, which will be very useful for us, and even for deriving the solution equations for the free underdamped systems. So we can have a reference of this later on. And one of the things which is important to remember here is, in a rotating vector form, we had seen that the velocity vector always occurs ahead, or it has a positive phase difference with respect to the displacement, and the value of the amplitude is omega a. If displacement vector is a, then the velocity has omega a, and acceleration amplitude has omega square a as the amplitude, and it is occurring earlier than displacement by half cycle, or 180 degrees, and velocity lags the acceleration by 90 degrees, right? So you will be coming across this relationship between the phase differences of displacement, velocity, acceleration. Okay, we have to revisit this when we create the vector polygon of forces in the chapter on force vibrations. So keep revisiting this chapter. Okay, so hope you have understood all the contents. Happy learning. Thank you.